started? Or?
Yeah.
Okay.
You can start, I'll go look for people upstairs.
Okay. Okay, hello everyone. Welcome back to the afternoon session. So this afternoon we will have a series of 30-minute talks with breaks in between. First we have Mendel Nguyen telling us about winding theta and semiclassical destructive interference. Excuse me. Take it away, Mendel.
Thank you. And thanks to the organizers for putting together this great workshop. So I'm going to be talking about the theta parameter and what happens when it's winding, and how to study it in semiclassics. Okay, so let me just start with some basic remarks about the theta angle. So whenever there's a continuous field in a quantum field theory that's classified by an integer topological charge, then we can find the theta parameter like this. We just modify the Boltzmann weight of a field configuration by e to the I theta times the topological charge. And from this we see that the partition function is 2 pi periodic. But it's not necessarily true that the ground state wave function is 2 pi periodic. And if that's the case, then even if the theory is trivially gapped for most values of theta, then there has to be some kind of phase transition as you dial theta from 0 to 2 pi. Now this has something to do with anomalies. And so for this kind of situation, what you can do is you can look at the partition function and turn on some background gauge fields for some symmetry. And then you look at the theta dependence of the partition function. And what you'll find is that when you shift theta by 2 pi, the partition function does not return back to itself, but it changes by some phase factor. And the phase being some local function of the background fields. And from this, we can see that the system at theta and at theta plus 2 pi are different as SPT states. Now an interesting consequence, a physical consequence from that is applies to interfaces from looking at a position-dependent theta angle. So consider this profile for the theta parameter as a function of space. On the left here we have theta constant at the value 0. On the right it's at the value 2 pi w, where w is just some integer. And in between, in some macroscopic region, it smoothly interpolates between these asymptotic values. Then in the region in between, we have an interface between distinct SPT phases. And by usual anomaly inflow arguments, you conclude that the anomaly on the interface is given by this, where this is actually just the w times the phase that you get in the change of the partition function at the top. So what I want to do in this talk is I want to study this kind of theta interface in a particularly simple setup that is semi-classically calculable. The theory I'm going to study is the two-dimensional CPN-1 model, formulated, compactified on a circle, a small circle with an appropriate symmetry twisted boundary condition, which I'll explain shortly. So just a reminder on this model, its action is given like this. It's got a unit vector field, an n-component complex vector, and it's got a U1 gauge field A, which is auxiliary, so you can integrate it out. if you like. It has a PSUN global symmetry. So if I multiply the Z with the SUN matrix, that's a symmetry. It's PSUN because multiplication by the center elements is equivalent to a U1 gauge transformation. And so that doesn't count. You have to divide out, therefore, by the center. And as on the previous slide, when you consider an interface of theta interpolating between the values 0 and 2 pi w, then you get this kind of anomaly where W2 of A being some background gauge field for the PSUN global symmetry. This is just some integer mod n, which depends on the gauge field.
What is background A in the action?
Background A?
A big A?
Yeah,
what
big A.
would it be in this case?
So this is something that you introduce.
How do you introduce it?
So you have to gauge the PSUN symmetry.
There's n of these. It's a different vector.
Oh, the D, the little d becomes a big D.
Yeah, basically. Yeah. Okay, and so from this anomaly, you conclude that the interface has to transform in a projective representation of PSUN with anality W. W again being
what is W2?
W2. It's some invariant of PSUN gauge fields. Second Steve Whitney class. Yeah.
Obstructions are lifted into an SEM.
Okay.
Yeah.
Right, you're integrating it
Over
through 2.
over 2.
What's 2 in the subscript? Is that
2D, yeah, 2D space. Yeah, it's a subscript 2. Yeah. Right. So it has to be in this projective representation. And
So again, could I ask, what does it mean that the interface is in a projective representation? Does it mean that the local operator is bound to the interface? They transform.
yeah. I mean, it's got a not right. So the interface has some non-trivial degrees of freedom. So it's some quantum mechanics. In this case, I'm studying a 2D theory. The interface is a point, so it's some quantum mechanics, and it's got to transform under the global symmetry, PSUN. But because of the anomaly, it's got to transform in a projective representation.
It just means it's in the fundamental of SUN.
It's in for example, yeah. If W is 1. Yeah. Okay. So I'm actually going to study, like I said before, I'm going to study this with a circle compactification and with a particular boundary condition. And the boundary condition is given by this. So I use this matrix C, which is an element of the symmetry group. And so I'm twisting the, along the circle, I'm twisting the fields by this symmetry element. It's a diagonal matrix with, I use the letter omega for the nth root of unity. Now, using a circle compactification is good for doing semiclassics because the theory is asymptotically free. If I have a small circle, then I can cut off the running of the gauge coupling. So not gauge coupling, the coupling constant. And I make the theory weakly coupled. But I want a bit more than that. So I'm not just taking the usual boundary condition, I'm taking some kind of twisted boundary condition. And there are many reasons to take such a twisted boundary condition. So one is that it's a boundary condition which is good for achieving adiabatic continuity. And this is the idea that if you want to study the theory at small circle, you want that theory to be continuously connected to the theory on R2, infinite R2. and this was due to Dunn and Unseld. Another reason is that this particular boundary condition preserves the two-dimensional anomaly. And that would not be the case if you just took periodic boundary conditions.
Doesn't it break the SUA?
It does, yeah, partially. So it changes the anomaly a little bit, but it still has.
It breaks into a bunch of U1s.
Yeah, I'll say what it breaks to in a moment.
Somehow the anomaly was all about PSUN versus
But
SUN.
right, but there's a essential part of that PSUN which survives. And lastly, this boundary condition was shown by Tim to be a necessary and sufficient condition for large n volume independence, which is the idea that the theory is equivalent to the theory on R2 at arbitrarily small circle. Okay, so now I'm going to come back to this. What is the symmetry when you impose this twist? And so PSUN is actually broken to this subgroup. So you've got U1 to the n minus 1. These are the diagonal elements. But you also have this product with Zn, which is somewhat less obvious. But this is the symmetry which is shifting. It's permuting the entries in the components of Z. And that's actually what's essential for getting this anomaly. The anomaly is a little bit different, but you still got it. It's now given by this two-dimensional classical action, which involves two Z-n gauge fields, A sub C and A sub S. I chose these subscripts because they correspond to clock and shift. And from this anomaly, you can conclude now that you need to get a projective representation of Zn cross Zn with anality W. And the minimal degeneracy, therefore, is given by n divided by the greatest common divisor of n and W.
I got confused. What are the two ZNs? Where did clock and shift go?
Oh, I'm sorry. So, yes. So there's a Zn subgroup in the UN to the n minus 1 part. So that is, and it's generated by this the C matrix, which is diagonal, like that. And then there's a shift, which is that second factor of Zn, which is cyclically permuting the entries in Z. And so I think of that as clock and shift.
Okay, I see. And the Z and U quotient bar is the diagonal of those two, but the point is the anomaly has to have something transforming the outward quotient.
Yes.
So the ZNU question is the phase, the linear phase. Clock and shift don't commute. They commute up to a ZN phase, so that's why it's a projective representation.
That's the quotient. It's the phase of the top relation.
Yeah, it's the phase of the clock and shift. You quotient back.
General question. So when you compactify the time for one of the directions to be a circle, how can you talk about projective representation anymore? It's like you have a just zero dimensional, not 0 plus 1, but 0 dimensional.
Just space.
Think of it as space.
0 plus 1.
So are you compactifying the direction where theta lies, or one perpendicular to that?
Oh, I see. I'm compactifying the direction with theta is winding. Yeah.
This symmetry is essentially implements
any boundary condition that z goes to cz. Like,
Something like that.
Is that
Why do you hope it doesn't break after?
No, I think you, so far, I mean, this is a separate story. You said you were going to put winding theta, but so far, these
So
ones
far, I
are just
haven't
about
yet. Yeah. So far.
boundary conditions on the CPN model.
Yeah. Yeah.
And I guess you're going to explain how you superimpose theta winding.
Yeah. So not yet. Not yet.
Yeah.
But that's where we'll get to. But yeah.
A capital W there.
Yeah, so here I'm sort of anticipating myself a little bit, because at this stage you can already say that this is going to be the anomaly on the interface, if you do consider it.
So as we don't have that much time, I suggest we just let Mendel keep going, and I think the W will become clear. You explained in a few slides what the W means exactly. Is that
Yeah.
correct? Yeah. Okay.
Okay, so I'm just going to explain some technicalities very briefly about this kind of boundary condition. So, what are the classical vacua? So, the first thing, I want to do a semiclassical analysis in this setup, so I have to figure out what are the classical ground states. So, we look for zero action configurations, and there turn out to be n of them. And they're given by this. They are and in terms of the gauge field, and I should have said that I should have given the formula for the gauge field, but you can characterize these ground state configurations by the holonomy of the U1 gauge field around the circle, and it's an nth root of unity. And so the n ground states just correspond to these distinct nth roots of unity, which the holonomy can take. This setup also implies the fractionalization of the topological charge. And what I mean by that is that this, which is usually an integer, is 1 over n times an integer. And we can find BPS solutions which achieve the tunneling between the various classical ground states, the n ground states. And so here I've written the explicit solution for the configuration which goes from 0 to 1. And the important thing about this formula is that, well, first, it satisfies the right boundary conditions. It depends on two moduli parameters, tau star, which is like the center of time of the instanton, and x star, which is a compact modulus, which runs over 0 to nl.
What's that?
Oh, I'm sorry, it's the length of the circle, circumference. Okay. Now our goal is to compute the transition amplitude between consecutive classical ground states. And if fractional instantons lift the degeneracy of these classical ground states, we should detect it by finding something non-zero for this amplitude, as we usually do, and as is the case when theta is constant. But it's different when theta is not constant, in particular when it winds. And to see this, we're going to have to be a little bit fussy about the boundary conditions. So when I compute this transition amplitude, I'm computing a path integral with fixed boundary conditions. on field configurations. Now, on the previous slide, I presented the solution in a particular gauge where the boundary conditions are not satisfied by a gauge transformation. There's a phase in the future boundary value which depends on the compact modulus. So I have to do a gauge transformation to get rid of it, because it makes no sense to integrate over configurations which differ, which have different boundary conditions. So if you do that, the effect is to shift the gauge field. Let's just pay attention to the gauge field. It just shifts by a term which depends on this compact modulus. This is, so doing this is essential, because before doing that gauge transformation, in this gauge, the gauge field just doesn't depend on the X star modulus. And we'll see in a moment that it's very crucial that it does. So now I want to talk a little bit about what it means for the theta term, for the theta to wind. And so we have to first talk about what it means. What does this symbol mean, theta dA mean? It's a little bit subtle, because theta is a circle value thing. The simplest way to treat it is just to define it as d theta wedge A. Now there's no ambiguity in theta. D theta is just a well-defined one form, and that makes sense as an integral. But now if I integrate this by parts, I see that I get the naive theta term, the naive expression for the theta term, plus some time-like Wilson loop with a charge given by the winding of theta. And this turns out to be part of this turns out to agree with this is a naive approach to a more sophisticated way of defining these kinds of theta terms with position-dependent theta. But anyway, under gauge transformations, this theta term does transform, but it transforms under gauge transformations that are large in time. So it's still invariant under small in time gauge transformations. Okay. Back to the instanton amplitude. I have to do this gauge transformation again because I had to fix the boundary condition. And when I do that, from what I just wrote on the previous slide, the theta term transforms. And I get a dependence, I get a term proportional to x star. And this contributes to the imaginary part of the fractional instanton action. And so when I compute the amplitude, I'm integrating over a phase factor, which gives 0. And this is the destructive interference of instantons. So this is, in this kind of funny way, this is how instantons actually achieve the cancellation, which you might have expected from anomalies. And in particular, for this, in this calculation, we see that there's an n-fold degeneracy, because we get, in this order, we get complete cancellation of all these consecutive tunnelings. 5 minutes. Okay. So this is my last slide. So why didn't we get the minimal degeneracy? So earlier I said that the minimal degeneracy is n divided by the GCD of n and w. That's the minimal thing that the anomaly requires. But we found n in leading semiclassical order. And it's natural to ask if, for cases where this GCD is greater than 1, if this n-fold degeneracy could be partially lifted. Maybe by looking at some higher orders in semiclassics. Well, in fact, this n-fold degeneracy is exact in semiclassics, and that's because there's a selection rule forbidding any transition between these classical ground states. The proof of that is actually embarrassingly simple. You look at the Noether charge for this symmetry. It's a U1 symmetry, a subgroup of the full symmetry. And it's generated by this matrix. Diagonal matrix with 1, 0, 1, 2, and so on the diagonal. If you just compute another charge, you get a term which is just what you get when theta is constant, plus an additional piece which depends on theta. And in particular, when you evaluate this on these classical ground states, you find that the state kth classical ground state has the charge W times K, charge which differs with K. If these states have different charges, then they cannot tunnel. And that's the reason for what we saw in the instanton calculation. Okay, well, I lost my conclusion slide, but well, I guess I'm just about out of time. Thank you.
Is it showing on your screen, or is it okay?
I messed it up.
Okay, no.
Okay,
Questions? Yeah.
Understanding you were talking the configuration at the end, was it with the boundary condition with the twist sheet matrices, or was it just a theta profile around the circle? Which one did you end up doing?
I'm sorry, I didn't understand the question.
What is the computation for which you actually did the computation?
Yeah, I used this boundary condition. All my computations were in that boundary condition.
Not with the theta shifting, or both?
With both, yeah.
Both in one direction.
Yeah.
Both in the
Oh, I see. In the direction. Yeah. So I'm string theory on a cylinder. The twist is along the cylinder, along the circle, and that's also the direction in which theta is winding.
I just don't completely understand why you need both. I'm confused.
Why do I not?
That nobody survives if you just do the shift and clock.
Well, that's right, but I'm interested specifically in the theta interface. I'm interested specifically in the situation where theta is winding. And the physics is different.
I think it's also true that it's just winding the theta without tweaking boundary condition. Yeah, we have not really analyzed.
Right, so why do you need both of them instead?
To do semi-classics. I mean,
just having a wide theta already guarantees some kind of theorem that there will be ground state degeneracy.
It's for the anomaly, right?
Yeah, just because it's an anomaly, right?
Yes.
So I just don't understand. It sounds like an number to do both.
well, I want to compute the exact number in semi-classics.
Yeah, maybe I don't understand.
Well, I mean, in your case, how many ground states do you have?
I mean, if you put me on the spot with just the theta winding, I would say it's n for 1 unit of winding and for 2 units of winding. It can depend on the radius of the circle. It can be 2n, or it can be n squared minus n over 2. It's a dynamical question.
It's a dynamical question, right? So I mean, so in this case, I find n, and that's it, right? So I mean, I can say for sure that it's just n.
Okay.
Why can't you compute it just with theta with a small circle? Is that not semiclassical? Just theta winding,
Yeah.
no twists of flavor, and small circles. Is that not semiclassical?
I mean, it is.
It's some kind of quantum mechanics.
Yeah.
Just look at the potentials.
Just small circle and quantum mechanics. Maybe it's not what we call a debugging. Maybe it violates a debugging continuity.
Well, I think that's true.
But in this case, actually, does the ACM once you want the n minus 1? Without twisted boundary condition, I think we get proof yes to the max.
Right.
Yeah,
So you have to ask that.
That's the other issue. You have that if you don't break SUN, the anomaly is fluid in class, right?
Yeah.
If you look at that anomaly with 2 units, then it must be a representation of SUN, which is not the SUN representation. So it has to have 2 boxes on that. So the degeneracy cannot be n. It has to be at least n squared minus 1.
Well,
there are no representations of SUN with n of dimension n and 2 boxes.
So this is because, well, yeah. So I've changed the problem slightly, right? Because
But I'm just saying that your final answer is not continuously connected to the theory with PSUN. It cannot be.
well, so I can't claim, of course, that number can be continuously connected.
Okay.
I agree with that.
So I think you lost the debate continuity more than this. Because it cannot be the right answer.
Well, that's true. Yeah, for this.
It cannot be the right answer.
For this, yeah. No, I mean, I mentioned it because it's a motivation for thinking about the boundary condition. It's a nice boundary condition. It's useful for many things.
When you construct your charge at the end, which also seems to make everything else superfluous, you need the clock matrix in there as well. You can just go to the slide.
We didn't see why you needed the twisted boundary conditions for this.
Well, that is because I want to be able to say. So that's because I wanted to be able to say that the ground states are. This is still a semi-classical calculation because I'm saying that I want to consider the transition amplitude between these n ground states, which I call k.
You're saying the charge is the same independent of the clock matrix, but the existence of the states themselves semi-classically.
Yes. Yeah.
I see.
Okay. Let's thank Mendel again. Now we have about a half an hour gap before coming back for, I believe,